models as well for neurodegenerative diseases.
Great. Well, thank you, Nick. This was really wonderful. You will see there are a couple of additional questions for you in the question and answer section.
Okay.
So you could answer those. Thanks again. Very inspiring. Congratulations.
Thank you very much. Look forward to C's talk. Bye.
Great. So I would love to now move on to our next awardee for the Robert Cotter Young Investigator Award. Congratulations to Dr. Si Wu. Dr. Wu received her Bachelor of Science in Chemistry at the Anhui University and her PhD in Analytical Chemistry at the Washington State University with Professor James Bruce. She conducted her postdoctoral research on top-down proteomics at the Pacific Northwest National Laboratory, PNNL, with Drs. Liliana Pazzatoli and Richard Smith. Later, she worked as a research scientist at Battelle Toxicology Northwest and as senior scientist at PNNL. In 2015, she joined the Department of Chemistry and Biochemistry at the University of Oklahoma as an assistant professor. Her research interest focuses on developing and applying high-throughput quantitative top-down proteomics techniques for addressing important clinical and biological questions. So I'm honored to have you here talk about your science today. I think it is very important for US HUPO to really express our congratulations to young scientists. So we're looking forward to your talk.
Thank you. Thank you, Brigitte, for the very nice introduction. First, I would like to thank US HUPO for honoring me with this prestigious award that is named after Dr. Cotter. And Dr. Cotter is known as a leading mass spectromist, a founding member of US HUPO, and most important, a great mentor to many young scientists. It's a great honor for me to share this award with Nick, one of my good friends in the field. I also want to thank my mentors. Jim convinced me that Jim is my PhD mentor. He kind of convinced me that mass spec is not a black box, and it's definitely boosted my confidence to open any mass spec instrument in front of me, which sometimes may not always be a good thing. I have been very fortunate to be able to work in Dick's group as a postdoc under Lily's mentorship. Although at that time, I have no clue what top-down proteomics is, especially for Lily. I have been working under her as a postdoc and later as a research scientist for almost 8 years. She has become a part of a family for me ever since. There's many other mentors in the mass spec field that I would like to thank, as well as at OU. It is impossible to count all the ways they have helped me in my career so far. So with that, I would like to start my presentation with one of the most commonly used example in top-down field. So if a protein has two possible post-translational modification site, like shown here, it can theoretically make 4 different proteoforms. With bottom-up approach, even if we can identify all the digestive peptides, it will be extremely difficult for us to know how many of these proteoforms are existing in the sample and their relative amount. With the top-down mass spec, we can easily answer this question by looking at the intact masses and their relative intensities. So if bottom-up mass spec can tell us this is a Swiss knife, and I believe top-down will tell us which function of this Swiss knife it has in a certain sample. So we believe that top-down proteomics can better characterize intact proteoforms, both qualitatively and quantitatively. As Nick mentioned, the top-down proteomics platform often include separation, mass spec detection, and data analysis. There are many challenges for using top-down proteomics approaches to study real biology samples, such as sample complexity, limited sizes of available samples, and needs for reliable quantitative method to study disease markers. So to overcome these challenges, we aim to develop a high throughput top-down proteomics platform so we can identify and quantify as many proteins as possible from biology samples. A simple way actually to increase the throughput of proteomics is to improve the LC separation performance. It has been reported that in proteomics, the number of identified proteins or peptides directly correlate to the separation performance or peak capacity of the LC. Therefore, in proteomics, better separation possibly give us more identification. As we know, reverse phase LC with packed columns is one of the most commonly used approaches in high throughput proteomics because it has mass spec compatible mobile phases and it is a very efficient separation method. And my research in the top-down mass spec field start with the famous long-packed capillary columns in Dick's group at PNNL with the help of many LC experts, such as Ray Zhao. We have optimized the C5 IPLC long column separation for top-down proteomics and used it in different applications. Just here are some of the examples. We have developed an integrated top-down and bottom-up mass spec platform. We also successfully detected a molecular switch of cysteine style modifications on bacteria growing under different conditions. To further improve the separation performance, we can possibly pack longer columns. However, there are many challenges for operating columns longer than 100 centimeter, such as higher packing pressure, higher operation pressure, and a low operation flow rate. To be able to successfully pack and operate these ultra-long columns, we need an automatic ultra-high pressure nanoflow LC system, which currently only one or two are commercially available so far. So at OU, we customize use the normal flow UPLC system from thermal, which can be operated at a pressure of 14,000 psi. We designed a double splitting system with only one additional valve. We were able to load the sample at 5 microliter per minute and run LC at 100 to 300 nanoliter per minute, only using one UPLC pump. Automatically at high operation pressure and such as 10,000 psi or higher. So our results suggested that our system can operate 100 centimeter or even longer column routinely and automatically without a very expensive nano UPLC system, which largely improved our top-down separation performance. So in addition, multi-dimensional LC separation is another way to improve the separation performance in proteomics. One of the popular approaches in bottom-up proteomics is the coupling of low pH RPLC and high pH RPLC separations. At different pH level, as we showed in this cartoon, the charge distribution on the peptide or protein will be different, and therefore the hydrophobic interactions between peptides and the beads will be different, providing relatively good orthogonality. The advantage of such two-dimensional separation method are it has a high resolution on both dimensions and provide clean samples for direct mass spec analysis. We have developed and optimized an offline 2D RPLC separation for top-down mass spec. We found that these two methods show very good orthogonality, which actually is better than the reported bottom-up separation orthogonality using the similar approach. One of the reasons is that proteins are much longer and the charge redistribution effects are much more significant. So using this two-dimensional separation method, we can detect more proteins and proteoforms. And here is an example of accurate carrier protein. This protein contains a cysteine that can be modified by a novel modification called phosphopentasiene. As you can see, in one-dimensional separation, it will has only one of the dominant proteoforms. And in the our two-dimensional separations, we start to see some low abundant proteoforms. As you can see here, some of the proteoforms on the sequence, such as with and without N-terminal removal, and also has the with and without this phosphopentasiene modifications. In addition, very interesting thing we found out, actually this phosphopentasiene has this free Sial group, and this free Sial group actually is very similar to the cysteine free Sial group. It can be modified by glutathione and it can also be oxidized. So overall, our two-dimensional separation platform allows us to detect low abundant proteoforms in biology samples. We also applied it to human cell lysate and were able to detect many proteoforms with PTMs, such as acetylation and phosphorylation. Here is just a quick example. In this glycine cleavage system H protein, we identified a known lipolysation modification on this lysine 107, after the cleavage of the N-terminal transient peptide, which is around the 48 amino acid length. In addition, we were able to identify a novel octanolation modification on the same site. And our results suggested this octanolation may serve as an intermediate of this lipolysation. Again, as we just mentioned, our two-dimensional RPLC separation performance is relatively good because it has a full orthogonality between the two separation forms, which make it an ideal method for online two-dimensional separation for low quantity biology samples, and especially our method can avoid the concatenation-based fractionation that has been commonly used for bottom-up approaches due to this good orthogonality. We have successfully modified our one-dimensional UPLC system into this 2D system with online dilution. It largely reduced our sample starting amount. Normally, we need 500 microgram cell lysate as our sample loading amount for offline two-dimensional separation, and here we can only use 5 microgram. We applied it to the E. coli cell lysate, and our results suggested that our online two-dimensional system provide comparable results to offline two-dimensional system with about 100 times less sample, from 500 to 5 microgram, which holds a great potential for small quantity sample analysis. Also, it has been reported that low volume sample handling can be beneficial for studying small quantity samples such as single cells. Therefore, a simple quantitative microsampling approach is often required. We have recently developed some a novel microsampling approach. We call it spray capillary, and it provides reproducible and quantitative microsampling using the electrode spray at this end as the driving force of the sample from this sample wire. And this sampling rate can be as low as 15 picoliter per second. And our spray capillary can directly serve as this capillary electrophoresis separation column for online separation and mass spec detection without any additional device. Just a simple move this sample end to the BGE buffer. It largely reduced the sample loss and improved the round-to-round reproducibility. We further modified our spray capillary, and for this sampling end, we put them into a taped-like tip with a size around 15 micrometer. Then we insert them into single onion cell. Our results show very good reproducibility for 2 seconds, 5 seconds, and 10 second injections on these single onion cells. Hundreds of metabolites were reproducibly identified and quantified across different sampling time points. We have developed some analytical techniques for sample handling and top-down. Now I would like to switch gears and show you how we apply our developed high-throughput top-down mass spec platform to study lupus and autoimmune disease, which is triggered by the environmental factor. Lupus patient can have abnormal immune response against the autoantigen and start to generate the autoantibodies. Currently, the diagnosis often happens after symptoms actually arise, and which at this point, many of these reversible organ damage may already occur, and it's very important to develop a method or technique that are capable of early diagnosis. We propose that actually an autoantibody, which is started at the very early stage, can potentially serve as a lupus biomarker. If we can detect these autoantibodies before these clinical symptoms arise, it can lead to therapeutic interventions preventing further organ damage. With it, we propose a platform for serum autoantibody study using top-down mass spec. As here, in brief, we separate and enrich the Fab fragment of serum antibodies and apply them to top-down mass spec analysis. And we use the targeted MS-MS, top-down MS-MS, and bottom-up sequencing for the intact Fab sequencing and characterization. So overall, here, as you can see, we can identify and separate many of these autoantibodies in this patient sample. We present a first top-down mass spec demonstration of human serum autoantibody pool analysis, which gave us a bird's-eye view for complexity of human serum autoantibodies. We also compare the serum antibody pools in healthy controls and the lupus patient serum. Many autoantibody monoclonal autoantibodies can be detected in the lupus patient, as we can see here. So next question is, if we can characterize some of these high abundant autoantibody as the disease biomarker. I will not go through the whole story, just quickly go through here. Combined with other techniques such as single BCL sequencing, we successfully identified a monoclonal autoantibody in the patient sample. The synthesized antibody shown actually very strong binding with the known autoantigen of lupus. For here is SMD, which can be a potential biomarker for the disease. Okay, just to give you a quick summary of our research at OU, there are some other very exciting projects in our lab that I do not have time to show you today, such as quantitative top-down mass spec using TMT, and some of the recent developed functional proteomics method. And some of them we will present them in the upcoming ASMS conference. With that, I would like to thank the people actually did the work. as Rudy mentioned this morning, research is a teamwork. I would like to thank all my students for their contributes to this presentation, especially Zhe, my first PhD graduate, who did many of the work I presented today, and Lu Shuang, who did the spray capillary work. And in addition, I would like to thank my collaborators, Ken, who is my collaborator on the Lupus project, and Xiaowen has been collaborating with me a long time for the software and development. And I would also like to thank funding and as well as the top-down community. Last but not least, I would like to thank you for being here, and hopefully everyone keeps staying safe and enjoy your time with your family. Okay, with that, I would like to start to take questions.
All right, thank you very much. This was really inspiring, I have to say. Thank you. I mean, it's very impressive to see also how chromatography really makes a big difference in mass spectrometry. We all know this. Yeah, so we will see. You know, maybe I'll just ask a very short question. I was interested in seeing, I mean, that's maybe difficult, but with your approach, is there any possibility of maybe also identifying new or unknown PTMs of mass shifts that you continue to see? I mean, that is probably also a bioinformatics challenge, but could you comment on that?
Yes, so actually that is one of the advantages for top-down proteomics, because lots of time for the top-down proteomics, we can like have multiple of the fragments that can have the similar like mass shift. And this mass shift can be either a combination of different type of PTM, and sometimes it can be like a novel type of post-translational modifications that may not be reported before, such as the one I showed over there. For the lipodization, like example. So for this case, like if all these fragments pointing to certain of the mass shift, we can manually evaluate and compare it with some literature. And although it's a lot of like manual work, but I think it's also like recently has been incorporated in some of the software development, such as Xiaowen's like topic software, and such as like Kelleher's group also has like many of the software that incorporate similar ideas. And I believe actually it's should be a advantage as well as a challenge for the top-down field.
Maybe very briefly, as we're running out of time, there's one question from Ying Zhu. Can you comment CE and RPLC for top-down proteomics?
Yeah, I think CE, we are just beginning to incorporate the CE to our separation. So definitely like much less like a sample like starting. And I know we are currently still have issues to getting very good separation for top down, but Liang Sun's group has a very good separations for top down. And for the reverse phase, one of the things is like it's very easy to handle, and the people has been doing it for so long time. So which means it will have lots of ways, like has been parameters has been pointed out that gave us the direction that we can use for improve our separation or improve our like sensitivity. So again, I think both of methods, the very nice thing for these two methods actually is complementary, mechanisms, so which makes them a very good method, potential method for online two-dimensional separation.
Sure. Thank you very much. Please go to the, you can also go to the question and answer section and maybe answer another question that just came in. I would like to congratulate both C and Nick, and thank you for being here today. And I'm turning over to Iliana for some closing comments for today.
Thank you, Birgit. So yes, we have reached the end of this wonderful webinar, and I will finish by congratulating again all of our awardees, including the awardees who presented last week, Steve Gigi and Jimmy Eng, and the awardees who presented beautiful talks today, Rudy Abersold, Si Wu, and Nick Young. Thank you all And I also thank all the speakers for generously donating their time and making these webinars a success. We thank, of course, the sponsors, our major sponsors, Bruker and SCIEX, who presented today, and Thermo Fisher Scientific and Shimadzu, who presented last week. We thank all the exhibitors, and I also want to thank all the attendees again. Obviously, this format is a little bit unusual, and it's harder to keep things on time, and there can be some tiny glitches, but really clearly this did not interfere with the ability to ask questions and interact and provide such a great platform to share research and findings. I want to also thank Conference Solutions, our management company, who joined US HUPO, joined forces with US HUPO just at the end of last year. And obviously you did not get the chance to meet them yet. Brianna, Jubilee, Jen, and Rainey, you're gonna get to meet them next year in Chicago. They're really wonderful, and they have put a lot of effort into making the US HUPO in Seattle possible, and also these webinars possible. I also thank again the organizers, and for all the hard work that they put in the Seattle conference that had to be canceled, and also the executive committee for their many conference calls every week, and for making these webinars really possible. But really thank you, the attendees. I encourage again everyone to submit e-posters. We will send you an email when we want to make these available in the same time. So we will send you an email that's going to be in a few days or so. And we are going to look for other opportunities to try to interact during 2020, during this year, and we will keep you updated. But in the same time, I will finish by saying, stay safe, stay healthy, and let's have a wonderful conference in Chicago in 2021. Thank you, everyone.